Normal distribution curve. What is normal distribution? Normal distribution is a type of continuous probability distribution. This concept is mainly applicable to continuous data, only except few distributions in discrete data, such as binomial and Poisson distribution, which also follows normal distribution. Normality forms an important consideration when calculating process capability measures of z-value and CP-CPK and PP-PPK. Additionally, normality is a critical decision factor when deciding which hypothesis test to be used in the analyze phase of Six Sigma project. Normality discussed. The concept of normal distribution was developed by Carl Friedrich Gauss, a German mathematician. He conceptualized normal distribution, where the distribution curve exhibited following characteristics. Let's talk about the key characteristics of a normal distribution. First, it's unimodal, meaning there's only one peak in the distribution. This represents the most frequent value. Next, the mean, median, and mode are all almost equal. This is because the curve is symmetrical, and the center point divides the curve into two mirror image halves. The peak of the curve always aligns with the mean, which is the highest point in the distribution. Also, it's important to note that the tails of the curve never touch the x-axis. They extend infinitely in both directions, getting closer and closer to the axis, but never actually reaching it. These are the foundational traits of a normal or bell-shaped distribution. Please note, the last characteristic, tails never touches x-axis, of normal distribution is probably the only limitation that the normal distribution has. Because of this limitation, normal curve will never represent 100% of the process. This image represents a normal distribution curve, often referred to as a bell curve because of its characteristic shape. The dashed vertical line in the center marks the mean of the distribution. In a normal distribution, the mean is also equal to the median and the mode, since the data is symmetrically distributed. You can see how the curve rises to its highest point at the mean, indicating that most data points are concentrated around this central value. The curve then tapers off equally on both sides, showing that as you move further away from the mean in either direction, the frequency of data points decreases. Importantly, the tails of the curve never touch the x-axis. They extend infinitely in both directions, reflecting the idea that extreme values, while rare, are still possible. This image shows a normal distribution curve with the concept of standard deviation illustrated. At the center, we have the mean, which also represents the peak of the curve. As discussed earlier, in a normal distribution, the mean is also equal to the median and mode. The two vertical lines marked as -1 sigma and +1 sigma represent one standard deviation below and above the mean, respectively. The area between these two lines, from -1 sigma to +1 sigma, covers approximately 68.26% of the total data. This means that in a normal distribution, about 2/3 of all observations lie within one standard deviation of the mean. This central range is critical in statistics because it highlights how most values are concentrated closely around the mean in a normally distributed data set. As you move further from the mean, toward +or -2 sigma and +or -3 sigma, you'll see even more of the data captured. But this image focuses specifically on the first standard deviation range. This diagram further illustrates the normal distribution curve and introduces the concept of standard deviation ranges. At the center is the mean, and from there we expand outward in both directions to show plus or minus 1 sigma and plus or minus 2 sigma, that is, 1 and 2 standard deviations away from the mean. The dark blue shaded region between negative 1 sigma and positive 1 sigma represents approximately 68.26% of the data. This tells us that about 2/3 of all observations fall within 1 standard deviation of the mean. Expanding further, the lighter shaded region, which covers from negative 2 sigma to positive 2 sigma, includes 95.44% of the data. So, nearly all of the data, more than 95%, lies within 2 standard deviations. This visualization is important because it helps us understand data variability and how normally distributed values cluster tightly around the mean, with fewer values as we move further out. This image illustrates the empirical rule, which helps us understand how data is spread in a normal distribution. At the center, we have the mean, and then we expand outward in both directions to show standard deviations, from negative 1 sigma to plus 3 sigma. The first range, from negative 1 sigma to positive 1 sigma, covers about 68.26% of the data. The second range, from negative 2 sigma to positive 2 sigma, includes around 95.44% of the data. The third range, from negative 3 sigma to positive 3 sigma, captures approximately 99.74% of all observations. This tells us that nearly all values in a normally distributed dataset fall within 3 standard deviations of the mean. These percentages are critical when identifying outliers, setting control limits, or evaluating process capability in quality control. Any data point beyond plus or minus 3 sigma is considered extremely rare or unusual in a normal distribution. This image shows a normal distribution curve overlaid with specification limits. LSL, lower specification limit, and USL, upper specification limit, marked by the red vertical lines. The mean lies at the center of the distribution, and the blue area represents the spread of the data within plus or minus 3 standard deviations. The LSL and USL define the acceptable range of variation for a product or process. Any values that fall outside these limits are considered defects or non-conforming outputs. A key takeaway here is that the process must be centered and tightly controlled so that the vast majority of data falls within the specification limits. This image sets the stage for discussing process capability. How well a process can produce output within these limits. Typically measured using metrics like CP and CPK. If you were to superimpose customer specifications, USL, LSL, you can get meaningful stats about process performance. Understanding specification limits. Spec limit. Specification limits are decided, mostly by customer. They may give you one-sided or two-sided specification. Sometime is self-imposed. As part of your offering, you give yourself some spec for performance. Law of the land can also specify acceptance tolerance area outside the specification limits are your failure area. This image clearly illustrates the importance of staying within specification limits in a manufacturing or process environment. We see a histogram overlaid with a normal distribution curve, showing how data is spread around the mean, which is marked with a dashed line at the center. On either side, we have the lower spec limit, LSL, and upper spec limit, USL. Any data points that fall outside these specification limits, highlighted in orange and marked as scrap, represent non-conforming products. In real-world terms, this means those products are either rejected, need rework, or result in waste, all of which add cost and reduce efficiency. This graphic reinforces a critical message. Any data point going beyond the specification limits is scrap. It's a strong visual reminder of why process control and capability are essential. To minimize variation and ensure nearly all products stay within spec. Understanding specification limits. Control limit. Control limits are decided by the data itself. You collect data, and your upper control limit and lower control limits are calculated from the data itself. Control limits are not provided by customer, and they represent process performance.